Hello, and welcome back to my YouTube channel. My name is Professor Gavala, and today we're going to be doing the fifth installment of EE220, where we're going to be talking specifically about equivalent circuits and source transformation. And we're going to start off by doing a KVL and KCL example. This is a follow-up from my previous video, so lecture 4. So if you haven't seen that, please go and check that out. So essentially we're going to be doing an example of KCL and KVL, where this was Kirchhoff current law and Kirchhoff voltage law, which is the fundamental laws for any electrical engineer to know. In addition, we're going to be talking about equivalent circuits. And this is the notion of we don't want to be dealing with a lot of schematics and when we talk about things. We want to be dealing with voltages, inputs and outputs. As a result, we kind of generalize all of our circuits into what we call an equivalent circuit. Additionally, we will talk about source transformation. And this is the ability to go from a voltage source to a current source, or transform a voltage source to a current source, and also transforming of a current source to a voltage source. Where this is the first example we have, and the first part of the example, it's a 7-part question, asks us to identify the loops and the nodes, where the first loop will be, and this is for our KVL, this is loop 1, and this is loop 2. And we can identify some currents here and say, based on loop 1, we have an I1, we have an I2, we have an I3, and we have an I4. And essentially, I0 plus I3 is equals to I4. And we're given these values here, I0, VO, R1, R2, R3, R4, and R5 as our resistance values. So we identified the loops, and then for the nodes, we're here. So this is going to be VA, and this is going to be VB, or let's do it lowercase b and lowercase a, VA. Okay, so that's it for the first part. For the second part, B, it tells us to write our KVL equations. And essentially we start here at V0 and we say minus V0, because again, you can think about it as loop 1 goes into the minus, and also I1 goes in through the minus. So we could say minus V0 plus I1 R1 plus I1 R2 plus I2 R3 is equals to 0. And this is at loop 1. And then let me change colors here. For loop 2, we could say minus I2 R3 plus I3 R4 plus R4 R5. Sorry. I4 R5 is equals to 0, and this is loop 2. And just to recap, I like to identify my inputs and outputs. So for example, this is plus minus. I consider a voltage drop across my resistors. So when I'm at loop 1, R3 looks like a voltage drop. But when I'm at loop 2, R3 looks like a voltage gain. So it's a plus to a minus. So plus minus plus minus. So this is exactly why here at my loop 2 equation, I2 is being subtracted. It's a negative because I'm gaining. I'm going down from negative to plus. And I3 is a positive because it's going from plus to minus. So it's entering the plus terminal and leaving out the minus terminal. And I4, again, is from plus to minus. So I hope that makes sense. It's a little bit of some pattern recognition, but these will be my KVL equations. The third part of the question is write your KCL equations. And for KCL, I1 minus I2 minus I3 is equals to 0. This is at node VA. And I3 minus I4 plus I0 is equals to 0. And this is at node VB. And you can see how we receive that, how we get that, because I1 is equals to I2 and I3. And essentially I4 is equals to I3 and I naught. All right. So and we talked about this in lecture 4. So this is just kind of review. So now what we can do is we can arrange this into a matrix form that says D arrange equation in matrix form. And essentially what happens is we can write 4 equations in respect to 4 unknowns and have an output. So we can write that R1 plus R2 times R3, 0 and 0. Let me space this a little bit better and use the entire page. R1 plus R2, R3, 0 and 0. And this is matrix from maybe an algebra class or a calculus class. We can write it in terms of this minus 0, 0, negative R3, R4, R5, 1, minus 1, minus 1, 0, 0, 0, 1, minus 1. And essentially what I'll do is I'll explain how we come up with these equations. So in this fourth equation, equation 4, 0 times I1 plus 0 times I2 plus 1 times I3 minus 1 times I4 gives us negative 0 because you move this to the other side. In terms of equation 3, 1 times I1, negative 1 times I2, negative 1 times I3 plus 0 times I4 gives us 0. If you were to do the same thing here in terms of equation 2, you would get 0. Let me change colors here. Maybe I'll do purple. 0 times I1, negative R3 times I2, R plus R4 times I3, and then plus R5 times I4 is equals to 0. And the same thing, I'll let the viewers to kind of decipher this one. Again, you move this VO to the other side, and that's where we get this VO from. And you get a matrix form. A is equals to A times the identity matrix is equals to B. And you could solve for this matrix using, and this is part E, matrix representation. You can solve for this using maybe MATLAB or a calculator or any online resource that solves matrices. And you get that I1 is equals to 1.1 amps, I2 is equals to 0.9 amps, I3 is equals to 0.2 amps, and I4 is equals to 1 amp. Next, it asks us to find the power in R5. So again, that's the power through this resistor right here. And we know the current flowing is I4, and the resistor value is R5. So simply put, P is equals to I4 squared times R5, which is equals to 1 squared, right? Because I4 is 1. 1 squared times 2.5, because R5 is 2.5, which is equals to 2.5 watts. We did this again in lesson 4. And then G, we have what is the node voltages, VA and VB, question mark. And essentially, VA is equals to I2 times R3, which is equals to 0.9 times 5, which is 4.5 volts. And VB is equals to I4 times R5, which is 1 times 2.5, which is equals to 2.5 volts. I don't necessarily write the units, but this is amps, and this is ohms, this is amps, and this is ohms. So I hope this concept of KVL and KCL makes sense from this example. And again, this is a very fundamental topic in electrical engineering. So make sure you understand this. Next, we'll move on to what are considered equivalent circuits. And essentially what equivalent circuits are, imagine if you have what's called the original circuit and you have what's called the rest of the circuit. And this could be like a load resistor or something like that. If you have a voltage V1 and a voltage V2 and a current I1 and a current coming out of it I2, we want to generate a simple equivalent circuit. A simple equivalent circuit. Again, this is the rest of the circuit. Where this is V1 and this is V2. Where again, similarly, I1 goes in and I2 comes out. Where we can consider the following. Imagine an example where we have five resistors. Five resistors, R1, R2, R3, R4, and R5. and you have a current going in, IS, we can break these down to voltages. So plus minus V1, plus minus V2, plus minus V3, plus minus V4, and plus minus V5. And we can write a KVL equivalent. And we could say that minus Vs plus R1IS plus R2IS plus R3IS plus R4IS plus R5IS is equals to 0. We can move the Vs to the other side, and essentially we have Vs times we have Vs is equals to R1 plus R2 plus R3 plus R4 plus R5 parentheses IS, which is equals to an R equivalent times IS, where R equivalent is considered the equivalent resistor, right? And this is R equivalent right here. So now we can draw our circuit like such. R equivalent Vs, this is Is, and we could say Is is equals to Vs over R equivalent. And the takeaway here is that in this case, this is what you would consider your original circuit in purple. And it has a bunch of resistors in it. But what, as engineers, we do is we just create an equivalent circuit which still has the same input, equivalent circuit, which still has the same input, Is, as the original circuit. And we do this a lot in engineering. For example, you have, which we'll discuss in later chapters, the op-amp circuit, where in this circuit is a bunch of transistors, but instead of drawing all these little transistors, we just consider it to be an op-amp that has 2 inputs and 1 output. So this is the ultimate equivalent circuit example for now that we can think about. And then we can consider an equation. We can introduce resistors in series here mathematically. We can introduce R equivalents for a series, for a in series resistor is the sum as I is equals to 1 to N of Ri. Again, this is resistors in series. As a side note, we want to introduce something called the voltage divider or voltage division, simply because it is important when discussing circuits. And in our example, in our previous example, if we were to ask what is the voltage across this resistor R2, well, we know Is and we know R2, so V2 is equals to R2 times IS. And this is R2 times this IS, which is VS over R equivalent. So essentially, we can say that the voltage across a resistor is equal to Vs multiplied by the ratio of its own resistance to the sum total R equivalent. And this is your voltage divisor equation. Or we can generalize it to say that VI of any resistor in series is Ri over R equivalent times Vs. Essentially, what we're saying here is that if I were to go and ask you to find R1, this would be R1 divided by R equivalent times Vs. And that's your voltage divider equation. It's a very big interview question where an interviewer will draw Vs and do this and tell you to find V out, tell you that this is R1 and this is R2. Let's say equals to 1 equals to 1. So V out is equals to 1 over 2 Vs. Or your V out is 50% of Vs. So if Vs is equals to 5, then V out is equals to 2.5. Now, we want to consider sources in series. So if we have the following, if an ideal current source, and so sources in series, a rule of thumb is that an ideal voltage source can be added in series, while an ideal current source cannot be added in series. So for example, and that makes sense in terms of if I have, this is, let's say, ground, and this is a current source and a current source, I1 is equals to I2. So you can't add them because they're the same thing. But if I have a voltage source and another voltage source, let's say V1 and V2, then the total voltage, V total, is equals to V1 plus V2. The total voltage between A and B, where this is B and this is A. Now, we want to talk about resistors and sources in parallel. So if we're given that there's a original circuit that looks like this, and we want to find an equivalent circuit of this, we could say that this is equivalent to a plus minus Vs goes into, this is terminal 1, terminal 2, 1, 2, goes into an R equivalent, which has the same current Is. So in order to analyze this, to go from this original circuit to this equivalent circuit, we can say that Is, this Is, is equals to I1 plus I2 plus I3. And by Ohm's law, I1 is equals to Vs over R1. I2 is equals to Vs over R2. And I3 R3 is equals to Vs over R3. And now we can say that Is is equals to Vs over R1 plus Vs over R2 plus Vs over R3, which is equals to 1 over R1 plus 1 over R2 plus 1 over R3 times Vs. And so we can say that Is is equals to 1 over an R equivalent times Vs, or Vs is equals to Is times an R equivalent, where let's not mistaken this R equivalent though for the in series R equivalent, because in this situation, and I'll write this down explicitly, resistors in parallel, R equivalent is equals to 1 over R1 plus 1 over R2 plus 1 over R3. All that inversed. And then we get 1 over R equivalent is equals to the sum of I is equals to 1 over N times 1 over Ri. So note that, again, you add the reciprocal. So you take 1 over R1, and then you add all those up, and then you take the reciprocal of that to get R equivalent. Now, we'll introduce current division. Current division is not as important as voltage division, but again, it's nice to see the proof of it, so you're introduced to it at least once. Where if we ask you to find I2, you would write I2 is equals to Vs over R2. And we know that Vs is equals to Is times R equivalent. So I2 is equals to Is times R equivalent over R2, which is equals to R equivalent over R2 times Is. Again, note that this I equivalent is talking about this one here, not the previous in series one we mentioned. But for a quick example, if you're given that there's a certain Is coming in here, and this is R1 and R2 and R2, and this goes down to I1 and this goes down to I2, we would say that Is goes to an R equivalent, which is equals to R1, and a shorthanded way to write in parallel is 2 slashes in between the resistors. And we'll prove that. So basically, and this is equals to R1, R2 over R1 plus R2. This is the equivalent resistance of 2 resistors in parallel. And it says that 1 over R1 plus 1 over R2 inverse is equals to R equivalent. So we get that this is R1 plus R2 over R1, R2. Inverse this, we get R1, R2 over R1 plus R2. And as you see, it's the same thing. These two are equal. So now we say that I1 is equals to, in terms of our equation, R equivalent over R1 Is. R equivalent is R1, R2 over R1 plus R2 times 1 over R1 times IS. This cancels out with this, and we are left with R2 over R1 plus R2 times IS. So this shorthanded form is your current divider. Current divider. And for I2, I'm not going to explicitly show how we get this, but essentially it's the resistor that it's not flowing through over the equivalent resistance, so R1 over R1 plus R2, or over the resistors added up times your input current. So this is, again, your current divider. The last topic I want to talk about for this video is called source transformation. And essentially, what is source transformation? I'm going to write out the definition. So source transformation states that a voltage source circuit and a current source circuit are considered equivalent and interchangeable if they deliver the same input current I and voltage V12 to an external circuit. And we should know what an equivalent circuit is now and an external circuit. But essentially, in terms of a diagram, we're saying that if you have a realistic voltage source, like a battery or a power supply, and it's connected to an external circuit, there's a voltage that's dropped V12, and there's a current that flows in it, I. This circuit is interchangeable to a circuit IS, or an ideal current source, which has a current source and a resistor R2 in parallel with it. Again, you have it connected to an external circuit. And again, you have to make sure that it receives the same voltage and the same current I, where we can consider this IS, and there's also a drop here, I2. Let's say this is also equals to I1. So IS equals I2 plus I1. But again, this I is the same as this I. These two I's are the same. And in order to satisfy this constraint, we can write a KVL of this loop here and say that minus Vs plus I R1 plus V12 is equals to 0, and I is equals to Vs over R1 minus V12 over R1. And we could write a KCL at this node right here. So we could write a KCL and say that IS coming in minus I1 leaving minus I2 leaving is equals to 0, where, again, this is equals to I. We could say I1, which is equals to I, is equals to IS minus I2, which is equals to IS minus V12 over R2. Again, because the voltage drop across this resistor is V12, because it's in parallel. So now, if we want to say that these two are equal, The equivalence for both circuits happens if and only if I is equals to Vs over R1 minus V12 over R1, and I is equals to Is minus V12 over R2. And essentially, this only happens when R1 is equals to R2 and Is is equals to Vs over R1. For example, if we said that this was, let's say this is equation 1 and this is equation 2, essentially I is equals to if let's say R1 is equals to R2, this is Vs over R2 minus, or we could say that this is equals to Is per this constraint minus V12 over R1, which means that it's equals to this I. Or if we wanted to go from this route, we could say I is equals to Vs over R1 minus V12 over R1, because again, keep in mind, R2 is equals to R1. So this only happens when R1 is equals to R2 and Is is equals to Vs over R1. So I hope that makes sense. We'll do a quick example here. So we'll do an example. So in this example, we're instructed to find I, which is the current through the 3 ohm resistor. These are in ohms. And essentially, using our methods of KCL and KVL, we can find I, but we want to kind of use the concept of source transformation and also equivalent circuits to find I, to kind of exercise our knowledge of source transformation and equivalent circuits. So what we're going to do is we're going to consider step 1 is convert IS1 and RS1 to a VS1 and an RS1. So VS1 is equals to IS1. Sorry about that. So VS1 is equals to IS1 times RS1, which is equals to 16 times 2, which is equals to 32 volts. So we can rewrite this as a new RS1 is equals to 2 ohms. So we keep that, and we say plus minus VS1 is equals to 32 volts. There's a 6 ohm resistor here from this guy, which also includes an 8 ohm resistor, which is, this is 3 ohms, this is 1 ohm, and this is I. Next thing we could do is we can combine. So step 2, combine RS1 in series with 6 ohm resistor. So we get RS2 is equals to 2 ohms plus 6 ohms is equals to 8 ohms. And then so we get an RS, we get a VS1, and now we have an RS2, which is equals to 8 ohms. And then now what we can do is step 3, convert VS1 RS2 back to a current source. This looks something like this. This is 8 ohms. Oops. This is 8 ohms. This is 1 ohm. This is 3 ohms. This IS2 is going to equal to 32 divided by 8, which is 4 amps. I hope that makes sense. And this parallel resistor, if we wanted to combine these in parallel, we would get 8 parallel 8. Remember, this is the parallel symbol. And if you do this, again, this is 8 plus 8 over 8 times 8, which is 16 over 64. Oops, made a mistake here. This should be 8 times 8 over 8 plus 8, which is 64 over 16, which is 4. And essentially, when we do another transformation, we get three ohms, 1 ohm, 4 ohm, plus minus, and this is VS2, which is equals to 4 times 4, because my current is 4, and my resistor in equivalent is 4, which is equals to 16 volts. And I is right here, and we know that if we wanted to find I, this is equals to VS2 over the equivalence, the equivalent resistance, or R equivalent, which is equals to 16 over 4 plus 1 plus 3, which is equals to 2 amps. So I hope that makes sense in terms of how we can use source transformation and equivalent circuits to kind of simplify our work from something that looks a bit complex like this, all the way down to something that's a little bit less intimidating, and get our currents. And from here, we can get our current I and find the current to the 1 ohm resistor and backtrack and get the resistance and the current and the voltage to the 8 ohm resistors, and so on and so forth. I hope that makes sense. Again, please like the video, subscribe, share the video. It's greatly appreciated, and it helps the algorithm. Thank you.